enolates. Okay, so that's the first actual reaction in this chapter. And that's the first reactions that we looked at when we first found the similarities between those reactions. So let's put it out first. The reaction is done under basic conditions. We're going to use sodium hydroxide, bromine. Your solvent will be water. And we already know what the first step is going to be. We'll abstract one of the acidic alpha protons, move electron density all the way on carbonyl oxygen. Form the enolate. The electron density will go back. And as it goes back, it will land on alpha carbon, which will attack the electrophilic, temporarily electrophilic bromine in dibromide molecule. Electron density goes to bromine. One of the bromines falls off as bromide anion. And we form the product. Okay. And we would assume that this is where reaction stops. So if we add just one equivalent of bromine, that should be good to form a monohalogenated product. In this case, brominated product. However, the reaction will spontaneously will be continuing until all of the hydrogens on alpha position are substituted with bromine. And the reason behind that is pretty simple. If we compare our product and the starting material, substrate, we can see that the protons here, your alpha protons in the substrate and alpha protons in the product differ in their acidity. If in the substrate, the electron density was pulled away by the carbonyl only, in here, the electron density from the alpha carbon is pulled away both by carbonyl and also by bromine. So these hydrogens are becoming much, I'm putting just a couple of pluses next to it. It's not a +2 charge, +2 partial charge. It just shows that we get a higher partial positive charge here. So the product becomes more reactive, and we already know what to do here. But I don't want to end up with the mix of mono, di, tri-substituted product. I would just swallow the bullet and say, well, I'm gonna let it go all the way to full bromination of alpha position, okay? So the reaction will continue here. So we're going to put excess of bromine under basic conditions. And again, the same steps will continue. So if I add my pentoxide, we'll deprotonate, break the bond, send the electrons on the carbonyl. And once the electron density goes back, we will get the next bromine on, and so on. So I'm not going to go show all the steps. Now our product is dibrominated. And with the next steps, I'm just going to put a couple of arrows here. We're going to get a fully brominated product. Okay. And of course, if we had alpha hydrogens on the other side, we would be getting substituted those, we'll be substituting those hydrogens with bromines as well. We actually take advantage of this reaction and qualitatively identify metal ketones by running this reaction. We call it iodoform reaction. So I believe I have the picture of it on the next slide. Oh, here it is. So I just want to show you the product and then we will go over the mechanism. Okay. Over here, as we see, we start with the metal ketone. So on one side of the carbonyl, we have a metal group. We add excess of 3 equivalents of iodine in basic solution. And then it follows by acidic treatment, and you get a precipitate of iodoform. It's a yellow precipitate. It's very easy to observe, so it's a good qualitative reaction. You can see that we are forming carcinogenic product, so we want to make sure that we are running the reaction in the hood. So I'm going to open a new page and show you the actual mechanism of this reaction. This reaction will give you, in the first step, reaction with 3 equivalents of iodine. And since we already went over the mechanism, there is no need to repeat the same steps. So I'm going to show you the product of the first step. We have fully iodinated alpha carbon. This is a metal ketone. Once all 3 positions, all 3 alpha hydrogens are removed, the product is fully iodinated on the metal side. We're going to continue with the reaction. You have base in the reaction mixture, so your hydroxy group will come back. And now that we don't have any alpha hydrogens available, the hydroxy group will act as a base and it will attack the carbonyl carbon. I will add as a nucleophile, attack the carbonyl carbon. So here we will see the first nucleophilic reaction of hydroxy group. And what happens here, guys? This fully iodinated metal group is becoming a really good living group. So when the carbonyl tries to close back into a double bond, it's possible, This group will leave. You will form a carboxylic acid plus your iodometal residue. And then in the second step, you will protonate your reaction mixture. And you will form iodomethane. The common name for iodomethane is iodoform. It's a yellow residue. Precipitate, and you will be able to distinctly see it if you have a metal ketone. And your iodomethane is highly carcinogenic. Okay. Now, can we run halogenation without actually going through polyhalogenation? And the answer is yes. But in this case, we will have to run the reaction under acidic conditions. So let's see if we can take a look at the mechanism of that reaction. Hopefully I opened the page for it in advance for you. Yes, I did. So this is acid catalyzed halogenation of enolates. We're going to look at a substrate here. Under acidic conditions, let's just put our generic hydronium ion. Always remember your acidic conditions are brought up by sulfuric, phosphoric, or toxic acids, one of those. In the first step, your carbonyl will pick up the protons. That will make the carbonyl carbon more electrophilic. And as a result, it will withdraw more electron density from adjacent alpha position. So it could more successfully react with, and we could more successfully react it with the acidic protons on the other side. So under these conditions, your water molecule will be able to pick up now more acidic proton. Electron density will run to this position, go back onto hydroxy group. We will recover our acid. Oh, what did I do? Okay, so then we're going to close this back on, move the electrons back onto carbon, and instead of moving them back onto carbon, let me pick up the bromines right away. And of course, it could happen from top or bottom, so we will be forming a racemic mixture. And we still have water here, or your bromide anion can pick up that proton. At this point, it really doesn't matter. And we're forming the final product. A racemic mixture. The reaction happens at this step because we have, in the last step, we're forming the most stable intermediate. Your oxygen is incomplete octet, is carrying a positive charge, but it's not an incomplete octet. So we have a stable intermediate. From that stable intermediate, we form a final product, and we are done with this. Okay? So if you want to monohalogenate, go through acid catalyzed reaction. And if you want to run a polyhalogenation reaction, you will prefer to use your basic conditions. Again, remember that you are going to choose, if you want to selectively remove protons only from a less substituted position, instead of a small base, you will use a larger base as LDA. Okay, so that is the first reaction. Next reaction that we looked at was reaction of your carbonyl compound from the alpha position with another carbonyl. And these reactions are called aldol reactions. So in aldol reaction, simple aldol reaction, your substrate is going to be an aldehyde or a ketone. If it's an aldehyde, it should carry an available alpha proton, and a ketone will be carrying, hopefully will be carrying at least one available proton